Welcome back to Gregory. Now we are going to model the zombie apocalypse, which will be useful to everyone, I think. This is the second video in a two-part series, so if you haven't seen the first one, please check it out. I think it would be helpful to understand what's going on in this video, because there I actually implement the machinery and ordinary differential equation solver and the disease model that will be basing this analysis on. But without further ado, let's jump into it. We'll have 4 categories and 4 equations in our ODE set. So we'll have the rate of change of susceptible humans, or this will just be humans. We'll have infected humans, and this is at some time t. We'll also have zombies, and we'll have, these are not recovered people, these are removed people. So these are either zombies killed by humans, or humans killed by zombies, or humans killed by humans. When you'll have an infected human and you know he's going to turn into a zombie at some point, you will be prone to kill him, I think. So equal signs everywhere. Now we'll allow our population to grow, and by that I don't necessarily mean that people move into an area, but zombies encountering more humans or something like that. So here we have sigma, which is human susceptible population growth. We'll also have a transition from susceptible to infected by zombie-human pairs, because zombies infect humans with the zombie virus, of course, and we will also be able to move to the removed state, which is delta S, delta subscript S, there we go, times this S. So, whoops. So now we'll see that here we'll have the beta S times Z. So this is how the infected population grows, and we also see that the removed people grow. So this represents people, susceptible humans, going to the removed category, and that means that they're killed by zombies or something like that. And we also have this category. So these are humans infected by zombies, right? Let's define another category. This is rho times number of infected. And this is the rate at which infected people turn into zombies. Okay, rho times infected. Can you see that? Cool. And we may also go from infected delta I. So all these deltas are when people move out of the population, they're dead, right? Delta I. And one last mode of transition, that's when zombies, call this alpha, killed by humans. So this is the zombie-human interaction, and then they are added to the removed group. Dead. Like so. Get it? I hope you do. Okay, so let's start building the model. To programming. Alright, let's go. So we need a new file. We'll call this SIZR for susceptible infected zombie removed.py. We need to import all our stuff. Numerical Python as np. We need to import matplotlib or pyplot, and we need our solver. So from ODE solver, import our forward Euler method. Okay, the simplest of integrating schemes. Okay, first of all, let's just we should probably do that up here. write down our equations so we know what we're doing. So the zombie apocalypse. Woo, cool. So S derivative is sigma, that's the population growth, minus beta, so this is the zombie infects human rate, minus delta S times S. Then we have the infected, which is beta times S times Z, so that's the same term as this thing, minus rho times I minus delta I times I, and Z, what do you say? Tell me in the comments. Rho times I minus alpha times S times Z. And the removed, or the dead, might as well call it D, but yeah, that's fine. Delta S times S plus delta I times I plus alpha times S times Z. So there we have all the dynamics of the problem. End the comment, hooray! So, class susceptible, infected, zombie, removed. We need a constructor, and this is going to contain a lot of things. We can just look at the equations. We need the population growth rate, sigma. We need the beta, which is the zombie infecting human rate, rho, which is infected people becoming zombie rate, and the zombies or people are removed from the population. Thanks. Yeah. And the initial conditions, S0, I0, Z0, and R0. That's it, I think. Yeah. So this is the zombie class. We need to indent it. There you go. Oh, there. Okay, initial values are S0, I0, Z0, and yeah, R0. There we go. All our parameters here, sigma, beta, rho, deltas, and the alpha, we want them to be able to vary in time. So we want to check each one of them if they're, so we start with sigma, is just a number, either a floating point value or an integer. And if it is, we define it as something that's callable. So later, when we try to pick a certain evaluated at a certain point in time, it'll work even though it was really a number. All right? So that's like that. Yeah. Or else, if it is callable, we'll simply set it as an attribute in the class, like so. Whoops. Okay, and we should copy this guy. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. So that's 1, 2, 3, 4, 5, 6. All right. So the second one is supposed to be containing beta. There we go. And the next one is supposed to be containing rho. Yeah. And here we have delta S, search, sigma, delta S, go. There we go. So let's correct the Selg thing. So now we are able to make these vary in time, which is a very nice attribute to have because we're going to make use of it later. And then we will also store the initial conditions, which will be S0, I0, whoops, Z0, and R0. Okay, I think that's everything we need. Now we just need to make this problem callable at some solution point and a time point. So this is the right hand side of system of ordinary differential equations. There we go. S-I Z R. Susceptible, infected, zombies, removed equals U. Or that's where you come from. Come from a land down under. As array. Yeah, so now we are going to return the value of our equations at this point. So we need to look at our equations up above. So this is what we want to return in 4 pieces as an array, 4 elements. So the first one is sigma minus beta times s times z minus delta underscore s times s. So that's, and all our sigma, all our parameters should be time dependent, so we can make it more dynamic. So remember that they're all stored here. That's what we did. I did all this stuff up here. Self dot beta t times s times z, whoops, plus self, whoops, self dot delta underscore s of t times, what was it? S, yeah. That's the susceptibles. And now we are moving on to the infected. So we have self dot beta t times s times c. We can just move up so see what we're doing. I remember this because I've done it before. So that's these terms, and then minus rho times I minus delta underscore I times I. Yeah. Minus self dot rho of t times I minus self dot delta underscore I of t times I. So that's great. Yeah, and the next one is the zombies. Is rho times I minus alpha times s times z, comma, self dot rho of t times I minus self dot alpha of t times s times z. Alright, last equation is delta s times s plus delta I times I plus alpha times s times z. A lot of stuff. Self dot delta underscore s of I times s plus self dot delta I of t times I self dot alpha there of t, and that was times I. I think that's it. I just saved it, so if something's wrong, oh, there's an error up here. What's going on? We're missing a colon. There we go. And now R is unused, so we'll just rewrite that to an underscore, so this editor won't complain. Good. We have everything we need. So let us try to define a problem. Let's start with some parameters. So I know that these work well, that's why I'm using them. So we'll set beta, which is the probability that a zombie infects a human. right? So that will be 0.0012. And we have alpha. Alpha is how likely a human is to kill a zombie. We set alpha to 0.0016. We're good at killing zombies. Yeah, good enough. Sigma, that's our population growth. We'll say that the zombies get to 2 more people for each time period. Yeah, that makes sense. And then rho, how many infected people go to zombies for each period. We'll set 1. Yeah, and then delta I is 0.014. Delta I is when infected are killed. So we do kill some humans that are infected. We'll learn that quickly, right? That this guy got the virus, kill him now before it turns into a zombie and kills the rest of us, right? Okay, what more do we have? We have delta S. Delta S is whenever a zombie kills a human. Yeah. Delta S, we'll just leave it as 0 for now. And then the initial condition. Number of people, 60 people. Not too many. The population is growing for every period. And no infected. Because we have 1 zombie. Patient 0. Right? And no removed, no dead people. And then we are ready to define our zombie model. Zombie model, SIZR. Sigma, beta, rho, delta S, delta I, alpha, S0, I0, and Z0. Yeah, one more, R0. There we go. And then we need a solver, which should be the forward Euler method. We'll insert the zombie model. Oh, zombie mode. Model, there we go. And we also want to set our initial conditions. Set initial conditions. And they are in the zombie model. Dot initial conditions. Hooray! And then we need some time steps. Oops. Time steps or time points, yeah, whatever. And now we want the time steps to be hours. This goes a bit quicker, so we'll say we let the model zombie apocalypse run for 24 hours. Relatively high precision. And we want to solve the problem, which gives us a set of solutions and a t. Solver.solve. So this is 0. Wait, time steps is going in there. Or time points. So I need to write steps. Good. Yeah, and then we want to plot our solutions. Hey. T, U, so 0, and that's label susceptible humans. There we go. And we also want to plot U1, and that's labeled as, that's infected humans. Infected humans. Alright. And we also want to plot 2, which is the zombies. And we'll plot the last thing. 3, that's our, well, that's the dead people. Dead people. Alright, and a legend to see the labels and show it. Now I'm very hopeful. Will it work on the first attempt? Python. did. But not much is going on here. We start with some susceptible humans, and then that rises, and then we have not much going on over here. Everything seems to in order. I think this is just very boring zombies. So let's try to increase the rate at which zombies infect humans. So we make them a bit more crazy, 10 times as more. Okay? Now we try calling the crypt again. Here we go. So now we see that we have a bunch of zombies and they win. Hooray! No, but this is interesting. So the susceptible humans, they get infected and they quickly turn into zombies, but after a while we don't have any humans left. We have some dead people. A very tragic end for humanity, but still more interesting than the other plot. But what we want to do now is we want to make the situation more dynamic, right? So let's write a movie plot. This will be very similar to The Night of the Living Dead, if you've seen the old classic. So we have 3 phases of our plot. The 3 phases of the zombie apocalypse. So, phase 1, the initial phase. This one lasts 4 hours, maybe? Yeah. It will be simple. Some humans meet one zombie. Right? And then more humans will get there eventually, so we'll have population growth, sigma equals 20. Beta, which is the infection rate, is quite high. Rho, when an hour passes, the infected turn into a zombie, so that will be 1. And we'll start with 60 humans. There. And just the 1 zombie. Okay, and yeah, that's it. Phase 2, we have hysteria. This one lasts 24 hours, and this is when the zombie threat is evident. Yeah, but now the infectious rate goes down a bit because people are running away, right? Alpha, we should do something with alpha. Alpha is zombies being killed, right? This thing. Some zombies should be killed in this hysteria phase, yeah. Delta I, that's infected being killed. So that was 0 here, and now we give it a value. So now it should be 0.014. Right, and we also have a population growth, but not that much. The zombies get to some humans, but not, 20 an hour, but 2 an hour, yeah. And row, how about row? Yeah, that's still 1. And then phase 3, which is counterattack. Hey. So this one lasts 5 hours, maybe? Yeah. And what's happening now is that we have alpha is 0.006, which means that we kill more zombies, right? Yeah, we kill more zombies, more zombies die. We have beta is 0, that means no humans are infected. Hooray! Countermeasures. Delta S, that's people getting killed by zombies, that still happens. Yeah, it's war after all. 0.007. Yeah. And row is still 1. Sick people turn into zombies eventually. There we go. Ignore these, and we want to implement functions for each variable. So first beta is the first thing we have here. Lambda t, that should be 003 if t is less than 4 hours. Else, okay, now we need to nest it because I want to show off my one-liner skills. Joke, why is Python a good stand-up comedian? Because it has so many good one-liners. So if t is larger than 4 hours, this is the second phase, and t 0.0012. Yeah. If less than 28, because this is 24 hours ahead, right? And else it should be 0.
Okay, alpha, lambda t, is nothing here. 0 if t less than 4. Else 0.0016 if t larger than 4 and t less than 28. Else 0.006. And then there's 4 more to go. Sigma is lambda t 20 if t less than 4. Else there's 2 and 0. Yeah. So it's 2 if t larger than 4 and t less than 28. Else
0. Okay, I kind of want to plot one of these just to see how it looks, so just make this linear space thing, and the hours all added up is 33, right? Yeah, 33 and 1,000 steps. Test list is... So we'll compute all the sigmas, say, in this list for t test list append sigma of t, and then we'll plot t test list. There we go. Yeah, here we go. So that's the kind of step function that we want, right? So here we see the population growth during the initial phase and the hysterical phase, and then the counterattack. Okay, good. That is satisfied. That. We go back up. This worked as intended. So rho is always 1, and then we have delta I equals lambda t. Delta I is 0 at first, t less than 4, else it's 0.014 if t larger than 4 and t less than 28, else what do we have? Now we kill infected people, so delta I equals 0.05. Yeah, that should do it. So let's change this, 0.05. Delta S, last variable, equals lambda t 0 if t is... No wait, oh, I didn't even look. Delta S is 0 if t is less than 4, else it is still 0 there. Yeah, so 28, else it should be 0.007. Cool. So I think we are ready to try. So let's see if we have any errors. None. Let's see if it works. Ah! This is so cool. Look at that. Ah! So the zombies get to more and more people. They are infected as this steep rise here, and this is obviously where the hysteria sets in, right? See that from the kinks, and then the population actually starts falling here. The zombies increase, but then we fight back and the zombies decrease. Yeah. We didn't do too well there, but we could play around with the variables or the parameters and see what happens. We don't kill that many, so let's try to increase the kill rate at the counterattack at the end. So we want alpha to be high, okay, at the end. So let's increase it tenfold. See what happens. Well, not that much, but this one should decrease more. But maybe because there aren't that many zombies. Oh, I know. I forgot to increase the time step to 33 because we're 33 hours total, right? Not 24, so we don't get past the hysteria phase. But I fixed it. Yay! Ah, there we go. Look at that, and then you see the hysteria phase, and then okay, counterattack, and we kill a bunch of zombies, and humans prevail. Thank you very much for watching this video. I hope you enjoyed it. Please subscribe and leave a like. I I hope to be able to make a bunch of computational or scientific computing examples in the future. See you in the next one.